Hello everyone, this is Group 8. In this video, we're going to talk about the mechanism of an important reaction happen in food process, the Maillard reaction. Maillard reaction is the non-enzymatic browning, which is widely used in food production. It usually refers to a series of complex reactions occurred between reducing sugars and amino acid or proteins in food. Generally, the Maillard reaction takes place when they are heated or at room temperature, then generate some flavor compounds and a dark brown pigment called melanoidin. As a result, Maillard reaction is responsible for the colors and the flavors of various food products such as baking products, coffee, steak, and chips. The reactions occurred during browning can be divided into three stages: the initial stage, intermediate stage, and the final stage. The initial stage involves with the reversible sugar amine condensation and irreversible Amadori rearrangement, while intermediate stage includes sugar dehydration, fragmentation, and Straker degradation. The final stage refers to the alkyl condensation and aldehyde amine polymerization. So let's move on to the initial stage. At the beginning of initial stage, the reducing sugar opens the ring with the presence of amino acid to form aldehyde. Then amine will add to the carbonyl group of it. The generated compound further loses a molecule of water to form and substitute glycosylamine. The following series of reactions called Amadori rearrangement, which is the isomerization of N-substitute glycosylamine to 1-amino 1-deoxy 2-ketosis. The N-substitute glycosylamine turns into cation of Schiff base under the catalysis of acid. Then it will undergo the deprotonation to form the ketose amines. The Amadori rearrangement is quite important for Maillard reaction because blocking this step is able to stop the browning.
After Amadori rearrangement, the Maillard reaction moves on to the intermediate stage, beginning with sugar dehydration. Due to strong reducing power, Amadori compounds can decompose into two ways under different pH environment. Under acid conditions, Amadori compounds undergo 1,2-enolization, followed by the formation of chief base by loss of one molecule of water. Then 3-deoxyzams is formed by losing amino group and obtaining one molecule of water. After a series of reactions, including second dehydration and cyclization, 3-deoxyzams lead to the formation of HMF, which is regarded as a marker of severe heating. Besides, there are two competing routes within the 1,2-enolization pathway, Paroline pathway and the beta-carbonyl route. The Paroline pathway leads to the perols, while the beta-carbonyl route leads to the formation of the isomeric compounds. The competitive ratio of these two pathways is 70:30, and further reactions will generate cereal-like and nutty aroma. Additionally, Amadori compounds undergo 2,3-enolization under neutral or alkaline conditions. This route can also be split into two pathways. Liberating amino group at C1 leads to 1-deoxy-2,3-decarbonyl, which lead to reductase pathway, while elimination of hydroxy group at C4 produce another decarbonyl compounds leading to furanocin pathway. Within reductase pathway, dehydration of 1-deoxy-2,3-decarbonyl gives rise to 3 furanones. Furanones were shown to be important for color as they are precursors of many colored compounds. Dihydropyranone is also produced and easily undergoes further reactions that lead to the formation of numerous compounds, some of them having flavor, color, and taste active properties. In parallel with reductase pathway, amino acetylfriends is produced by cyclization and dehydration with furanocin pathway. This compound can easily undergo further reactions such as oxidation and condensation. Visible browning hasn't begun during the intermediate stage. but a strong absorption in the ultraviolet range can be detected, indicate conjugated unsaturation contributed by sugar dehydration. Besides, many reactive intermediates are produced. These intermediates can further react with amino acid by condensation, cyclization, and polymerization to form melanoidin.
Okay, let's move on to sugar fragmentation and Straker degradation. Firstly, I'm going to talk about sugar fragmentation. The sugar fragmentation products vary considerably in their potential for browning. Generally, retroaldehydzation is thought to play an important role in sugar fragmentation. Moreover, oxidative fission also has a positive effect on sugar fragmentation. Sugar fragments can be produced by the following reaction respectively. Part 1. The amidori compounds directly gives dihydroxyacetone and glyceraldehyde through the retroaldehydzation and subsequent deamination. Part 2. The intermediate compounds can be formed by the 2,3 enolization of the amidori compound. Next, the intermediate compounds will give pyruvaldehyde and glyceraldehyde and glucoaldehyde by the retroaldehydations. Acetic acid will be given by oxidative fission. Moreover, butyrione and acetic acid also can be produced by arrangement of the intermediate compounds and subsequent reductions and hydrolysis. Part 3. The 1,2 enolization of amidori compounds will give 3 deoxysomes, and these compounds will produce 2 oxypropanols, glyceraldehyde, glucoaldehyde, and formaldehyde, which inhibit the browning by a series of reactions, including retroaldehydzation. Actually, fragments which include the alpha-hydroxycarbonyl grouping will undergo browning alone, but browning is accelerated in the presence of amino compounds. Well, secondly, let's talk about Straker degradation. The mechanism is that alpha amino acid liberated in the degradation of amino acid by glucose or other sugar, and can produce carbon dioxide and aldehyde. There are 2 pathways can cause browning. Firstly, the aldehyde formed by the Straker degradation are a source of browning. And the hydroreductones pick up nitrogens from the amino acid can cause browning.
Okay, hello everyone. In my part, I will introduce the final stage of Maillard reaction. It's involving 2 parts, aldehyde condensation and aldehyde amine polymerization and forming heterocyclic nitrogen compounds. The final stage of the Maillard reaction is consistent by the polymerizing intermediates and the forming unsaturated and colored polymers. The main reactions involves aldehyde condensation and aldehyde amine polymerization and forming heterocyclic nitrogen compounds. Okay, I will introduce the final stage in the 2 parts. This diagram apparently shows this final stage. Okay, firstly, amino compounds can effectively catalyze the aldehyde condensation of acetaldehyde and chlorophenoldehyde. Due to the amino catalyst and the generation of aldehydes by sugar dehydration, by sugar fission, and by the Straker degradation. Obviously, aldehyde condensation is chief cause for the melanin formation. The second part is to polymerize aldehyde amine or even acetaldehyde and ammonia. Finally, can form the polymeric colored products at a low temperature with unknown structures. Okay, I have listed some tests about this part. Patrick thought melanin contains the pyridines by testing the reaction between aliphatic aldehyde and aldehydes. Second, Paulis and Elson Morgan found the presence of nitrogenous heterocyclic compounds and concluded the similar spectra between the fluorescence and pearl by heating solutions of the sugars with the amino acids. In conclusion, we have introduced the mechanism of Maillard reaction in 3 stages, including initial stage. It involves colorless and no absorption in near ultraviolet, and then intermediate stage has colorless or yellow with a strong absorption in near ultraviolet. The final stage is highly colored.